let's begin with the questions from last time. So the first question is, in the real world, life does not always go as planned. How can an LLM address the problems while doing planning? So there are many ways you can do this. One way is to keep feeding it real-time information so that the LLM can adjust and give appropriate recommendation to the new information. The second one is that as it gets more exposed to more data over time, the LLM can improve with the planning on real-time feedback. The third one is that you can also use human-in-the-loop approaches so that it can learn like the human experience and human intuition and hopefully come up with a better plan. Well, the answers are not exclusive to these. There are many more. And for the second question, some approaches of LLM planning list many actions and select from them, which incurs a lot of computational cost. What are ways that we can reduce them? So one way is that you can eliminate some of the less promising actions by using heuristics or some other rules and make sure that there are less things to consider. Second is you can cache the results of things that are common so you don't have to recalculate them all over again. And finally, instead of evaluating everything simultaneously, we can do them incrementally and then decide at every increment whether or not we should continue doing calculations. Any questions so far? Any from the chat? All right then, so let's get into today's topic. My name is Nick, and this is Can LLMs Remember? So in order to begin, let's play a game. So I'm going to show you a series of numbers, and some of them are going to repeat, but not the one right next to it, but I want you to say repeat only if you've seen that number 3 steps ago. So if I show you 1, 2, 3, then a 1 again, I want you to say repeat at the 1. Everyone clear? Okay, let's go.
Repeat.
Okay.
Repeat. Repeat.
Repeat. Repeat.
Repeat.
Okay, how many repeats did you get? Okay, I might have actually spoiled it. There are actually 6 repeats in this number, in these like series of numbers. Seems difficult, doesn't it? So what we just did is something called the n-back task, where n refers to how much further back do we have to sort of remember things. And this is one way that we use to measure memory. So the reason why I want you to play this game is that let's think to our main question. How do we normally test LLM memory? Or maybe sort of like, maybe a better question is, how do we normally test an LLM's memory? So usually what people tend to do with LLMs, including myself, is I just sort of like ask it to recall some random facts, like who was the first president of the United States? And of course, ChatGPT knows what is going on. However, if you think about it, what we just did in the game, it seems to be one kind of memory. It seems to be like recalling things that are used for a short period of time, whereas the ones I asked ChatGPT is asking about different facts and things that you might remember long after it occurs. So why is this? Well, because memory is complicated. There are a lot of kinds of memory. In fact, here is sort of the taxonomy of human memory according to psychologists. So on the far end, over here, we have working memory. These is also known as short-term memory, things that we use for a short period of time. To the right, we have long-term memory, things that we remember for, well, long periods of time. However, we can subdivide these into two more subcategories: declarative and non-declarative, or explicit and implicit. And this really depends on whether or not we are really aware of it. On the right side here, the reason why it is implicit, for example, things such as conditioning, you might recall this famous story of Pavlov's dog, where we have like a dog, we give it food, we ring a bell, and then after a while it learns to associate between the food and the bell. It might not be like consciously aware that the bell has anything to do with the food. However, through this process of conditioning, it is able, whenever we ring the bell, start salivating. This right part here, because it's really hard to determine what do we mean by things we know we're not really conscious or aware of in terms of LLMs. I'm just going to pretend this side here doesn't exist for the purposes of this lecture. Now, on the declarative or the explicit side, we have memory that are related to events, also known as episodic memory, as well as things that relate to general facts, also known as semantic memory. So, in this one, as I said before, I'll be focusing on these three: working memory, episodic memory, and semantic memory, and try to compare between humans and LLMs to see whether or not it has some kind of equivalence. Any questions so far? Okay, so let's dive into working memory. So working memory is a system of maintaining and manipulating active representations. It is about things that you're currently working on, things that you need to remember in order to do a task. For example, the task we just did. So the properties of these memory is that they're very quick to recall. But it also comes with quite a few drawbacks, which is it has limited capacity. According to research, we have this sort of like rule of thumb where we say that humans can remember about 7 things plus minus 2, or the equivalent is something you can say in about 2 seconds. Now, the reason why this thing is really vague is because it doesn't really matter what those items are. So one trick that memory athletes do when they try to remember like huge amounts of data is they sort of like chunk things up into like bigger items, or leverage something in the long-term memory in order to be able to remember something a lot more. That is more of a fun fact. And finally, working memory is quick to forget. How quick? Well, does anybody remember what was the 4th number in the NBAC game? Well, neither do I. So let's just go on. So what are the ways that we use to test working memory in humans? One way is to use the span test, which is the number of items that can be recalled with at least 50% accuracy. So as you can see, as the number goes longer and longer, it's probably going to be very hard for the average human to sort of remember. The other one is the NBAC task, the thing that we do, the thing that we've been doing at the beginning of the activity. So what is the human performance, at least for the NBAC task? For the span task, we know it's about 7 things. As you can see, as the number of n, or how much further back you go, performance deteriorate quite rapidly. Like by the time you get to 3 back, people are at around like 60 to 70%. And the performance get even lower if we make the task harder. For example, this thing here, the visual dual task. So instead of just remembering numbers, you also have to remember colors. So the color might be either blue or orange, and then if they match, then you have to say the color matches or the numbers matches. It gets really difficult. Now, to the question, what about LLMs? So for the span task, it's pretty easy. I just sort of like shove a very long number into ChatGPT and ask, can you recall this? And of course, it was able to do it really well. It could even sort of recite it backwards with absolutely no problem. So it seems to be doing really well. However, I also tried doing the 3 backtask, the exact same numbers that you just did. So I prompted, okay, you would do a 3 backtasks and repeat blah, 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 and then I start the task. It was able to get 4 of them correct, but it also had 3 false reports. Not so great there. I was thinking, okay, maybe it misunderstood what was going on because like after I set the 6, it was saying understood. So I tried again. I made sure that it really knows what it's doing. I say, okay, what is the end back task? Okay, you will do this. I tried to let them confirm that I will begin starting the task now. It did even worse. So it's really curious to see why. Why is it that it's not doing that well? And I'll actually leave this question to be one of the end of lecture questions that we'll be answering next week. But I will next explain why am I so confused about this. So in order to answer this, I need to first go into what are LLMs actually doing? In particular, what is the language modeling task? Hence the LM section. Okay. Okay, there's an AI system there. Anyways, so if you see the task of language modeling is you have a context, sort of like the text that comes before, and using this information, you want to predict what is the next word. For example, if I see Mary had a little blank, as you might all know from the famous nursery rhyme, the word is probably lamb. So we can so the reason why it is able to do this, especially in the GPT models, is that it uses the attention mechanism, in particular the causal attention variant, where the LLM is able to look into all of the words, calculate how important each word is to the current task, and then use that information in order to synthesize a prediction of what the next word should be. So we could sort of think of this context as some kind of working memory. And there are multiple similarities to human working memory. For example, it could be short term. For example, if I just casually wipe out this context, the LLM wouldn't be none the wiser as to what happened so far. And also, there are some limitations because in attention mechanisms, like you don't, as the context is longer and longer, the cost for calculating gets longer. So most people tend to sort of limit how much can you go. So it is also limited and finite, which is kind of similar to how working memory is. So does LLMs have working memory? Yes, and it could, emphasis on could be better than humans, because some of the largest models that we have in the public market is that we could have up to 32,000 tokens of context. Like we can have something that is very, very long, and it could potentially remember and understand everything, which is why I was really confused when I tried the NBAC task as to why it was failing so much. And that will be a question for next week. I'll be asking you at the end. All right, then. Let's move over from the realm of temporary working memory all the way to the realm of long-term memory. If you remember, there is the long-term memory, declarative, and then now it's going to be the subtype of episodic memory. So episodic memory are memories about events. In particular, they're about co-occurring features in space and time. Anything you could sort of say as a what, a when, or a where. So think of things like, okay, what happened after you had lunch yesterday? What happened during last lecture? These are all things that are episodic memory. So episodic memory is always tagged with spatial and temporal context. So if you think about an event, you can always sort of say, oh, it happened at this time and at this place. Second property is that it is experienced personally. Like you can only have experiences of events that you experience. Now you might argue, wait, what about if my friend told me about about this cool event that happened to them. Well, then that's actually not experiencing it, but is rather your own reconstruction of that memory from what you hear from your friend. So it's not exactly experiencing that kind of memory. And finally, the other cool thing about episodic memory is that it is learned in a single exposure. So the main difference from, say, working memory and what I will explain later in semantic memory is that events don't really repeat. You just expose it once, and then somehow, oh, you remember it. Some other properties of episodic memory is that it degrades with time and new information. So let's just say I give a talk on this podium like multiple times, like 10 times. Each time I come to give a talk on something similar, the more of my information about the first talk will start to degrade. And as time passed, more and more of that information would gradually erode away. But okay, what if you saw a dream and could someone repeat that question, please?
Saw a dream and remembered it.
Does that count?
As experiencing it?
Yes, it sort of counts as experiencing it. There are research into dreams as to like exactly what it's doing. Some people say that it is actually something called sleep dependent. I forgot the exact term, but it's about synaptic replay. It's about replaying memories, which is one way that the brain moves things from short-term memory into long-term memory. There's a lot of research and detail into that, although I do not know on the top of my head. But yes, it is a kind of experiencing. So, okay, so we've talked about how it degrades. But you might wonder, okay, when I recall something, I sort of seem to have all these like different information. Wouldn't my memory be all spotty if like it degrades over time? Well, our brain compensates for that by reconstructing the missing pieces. And sometimes these can lead to memory errors. For example, and these are very important for things such as court cases. There are a lot of accounts where people have false memories. They thought something had happened, even though it didn't. They were accusing people, even though they were nowhere there once the evidence came out, and many other things. Finally, emotions will also affect how vividly you remember the emotion, but not how accurate they are. So one of the main things that people tend to do in research study is, for example, like the 9/11 event, where like people were like really shocked about it, and a lot of people can remember it in huge detail. However, there are cases where it just falls apart. For example, they interviewed the president, and then they try interviewing him again a year later, and they found out that the two recounts like had a lot of contradictions. Okay, so enough on the human side. What about LLMs? So after doing the n-back task, I decided to try asking it, okay, what happened in our conversation so far? And it seems to be able to remember exactly what happened. So how does it do that? So let's revisit the language modeling task, and that there's a context and you're trying to predict something new. One thing that I left out in here is that in many sort of like multi-turn, so like chat style, like language models, is that they also have the tokens from the past turn as well as some other information that they use. For example, even though the current sentence about Mary had a little blank, but if in the context somewhere in the past they talk about Mary having a donkey, then instead of a lamb, the LLM would know that they're actually talking about a donkey and not a lamb. So we could say that not only is this context sort of analogous to working memory, but it could also sort of be analogous to what episodic memory is. However, in LLMs, the lines are a little bit more blurred because, for example, in human memory, the short-term memory is sort of like more associated with a brain called the hippocampus, whereas longer-term memory is sort of consolidated in other parts of the brain. Whereas this one, there isn't really like a clear line between the two. Also, another limitation is that eventually we will run out of context. And using LLMs alone without any other tricks, if we just like keep giving it more and more and more information, eventually it'll just run out and start forgetting things. So if this person started ranting to this poor LLM here, eventually you'll start forgetting what happens earlier, or it will just simply not being able to function without specific tricks, which we will discuss next time in Lokman's lecture. So, do LLMs have episodic memory? It's quite unclear as to like what it is. Okay, final part. Final part in terms of memory. Semantic memory. So semantic memory is about facts. So if you remember this here, I asked ChatGPT, who was the first president of the United States, and it is able to recall certain facts correctly. Now, the main difference between episodic and semantic memory is that semantic memory isn't really tied to any context. There's no space, there's no time. Like if you talk about like remembering who's the first president of the United States is, you're not going to remember like, oh, I learned this in this grade by this teacher at this time. You just remember that, oh, it's this person. So it is about facts that you know. And because it is devoid of context, it can be gained information from someone else. So it doesn't matter whether or not you read about it, you read it on the website, you learned it in the classroom, or just some random person told you. It is similar. For the same reason, semantic memory are the type of memory that is strengthened with repetition. So unlike the case where if you do the same things over and over again in episodic memory, you start to lose the details. For semantic memory, you start to strengthen how your memory of it. In fact, there are some people who theorize about the difference between semantic and episodic memory is that as you get more and more episodic memories about the same thing, your brain gradually removes all the context, and what you're left with is semantic memory. And finally, semantic memory can also include statistical memory, sort of like facts about language as well as other things. You can see this working by seeing which one sounds more natural between the word TikTok and the word talk-tick. To most English speakers, TikTok definitely sounds better. And that is because the progression of vowels in English tends to follow tick-tock more than talk-tick. And this skill is really important, especially in infants who are learning language. And research has shown that they are very sensitive to learning this. You can read more. If you're curious on any of the sort of like psychological parts, I recommend you can try reading the textbook of Learning and Memory, which is in the references of this presentation. Okay, back to LLMs. Do LLMs have semantic memory? In order to answer this question, let's go back and look at the way that LLMs are trained. So the way it works is you have a bunch of text, and then you sort of like ignore the later parts of the text. These are simplified, of course. Then you pass it through the neural network, which is represented over here, and then you try to train it such that it can give the correct output. However, in the process of doing this, it has to sort of learn these semantic facts. For example, if you see the term like first president of the United States, you should sort of know, the model should learn somehow that that is related to George Washington, for example. And this includes many other things that are related to semantic memory. So we could argue that the information is sort of stored within the parameters of the model. And this is very different from the other two types of memory that we have discussed so far, which are more sort of encoded in the context version. As you can see, this one is like tied to the model, and you can't really change it after it is trained. However, despite the LLMs being touted as some of the next generation of searches, as well as like helping people with their homework, among with other things, it is not perfect. I have tried asking it to recite the 5th paragraph, not the first. It is usually very good with the first paragraph of the book Frankenstein. So it outputs a paragraph. I checked it. It matches exactly to the text, like word for word. There is nothing wrong with it, except it's from the wrong chapter. This is actually from in the middle of the 7th chapter, where I was actually asking for the 5th paragraph in the 1st chapter. So that was weird. So I looked at the 2 paragraphs and found that, oh, actually, both of them seems to have very similar beginnings. It's just that while the LLM was producing text, and due to the way it's constructed, which is being autoregressive, which is fancy terms for saying that it produces word by word, and once it commits to a word, there is no going back. So what probably happened is that ChatGPT says, okay, I remember the 5th paragraph is probably starts with 6 years, and then it just fumbled between the word have and had. And once it started going to the, so once it had, oh, given this is probably elapsed, and then it just went off the rails from there. Also, some of the models have been known to be misleaded by questions. This happened in early of January of last year, where someone used GPT-4 right after it came out, and then they asked, who was the sole survivor of the Titanic? For context, there were actually 706 people who survived. However, ChatGPT just seems to just sort of like go with the flow and then say, oh, this is the sole survivor and stuff. And later on, if you go into this article, he tried saying, yeah, do you know that could you cite the reference where there's only a single survivor? And then ChatGPT was like, oh, sorry, I was wrong. There are actually this many people who survived. Just so you know, before you actually go try this, I've tried this myself, and this no longer works. It has long since been corrected. So as you can see, even though it is able to recall semantic facts, it can be flawed. And a lot of times this is actually matching with what humans do. Like if you, like for example, if you go to a test, like you're not going to recall everything that you have studied so hard perfectly. And sometimes we have seen cases where a misleading question is able to induce like false memories, although those are more on the episodic side. I forgot the name of it on the top of my head, but there was a case of a child care center where the interviewers asked them very suggestively about shady things that were going on there. And what the interviewees answered ranged from accusing them of doing some child abuse acts that didn't happen after investigation, or even accusing them that they were using them for some kind of satanic ritual, which was a very odd thing. So, okay, tangents aside, so do LLMs have semantic memory? The answer is yes. But they also have the same flaws that humans have when they try to recall things. Now, so on to the next part. This is going to be more on like how do we address it in more of like with classical, well, classical as in like pre-LLM style things. And one of the big questions that you might have is that, okay, if our memory is flawed, what about writing things down or reading from a book or something, like things that don't really change and don't really affect the outcome? So this goes into the last part, which is on information retrieval, the classic way. So information retrieval is a field of study where we have a bunch of documents, we have something we want to search for, and we try to match the two. So if we think about this naively, one way is that we could just simply take the query that we have, and we just sort of like look through each document one by one, saying, this word matches here, this word matches here. But we would have to scan through all the documents every single time we want to search for something. And that is very inefficient. So one way that a lot of information retrieval systems do, including Elasticsearch, OpenSearch, and many of the things that are built on top of a system called Apache Lucene, technicalities aside, are using something that is called a reverse index. So what a reverse index is that we have a bunch of terms, and then we map them to where do they appear in each of the documents. And using some fancy indexing, we're able to chain together these things and actually search for phrases. You could go a step further by saying that, OK, I not only do want to search the terms, but I also want to have synonyms. You could have like a list of synonyms and sort of like match the two of them. Now, this seems good, but what if some of the words are missing in the query and vice versa? Or if there's some word that is in the middle of the document that doesn't really appear in the query? So this is where statistical algorithms come in. And one of the most popular ones, which is also used in systems such as Elasticsearch, is the BM25 algorithm. Now, this kind of looks complicated, so here's a very high-level explanation about it. So the first thing is, instead of sort of like trying to see if the phrases match exactly, or just do some blind counting. So first we do the top term, which is we try to count the co-occurrence of words in the query and the document. We assume that if they co-occur more, then it's probably going to be more relevant. However, there are words such as a, and, the that are like very common in all documents and is going to co-occur a lot, but it doesn't really give us any information. So we have the term to the left, which is we try to weight words, upweight infrequent words. So this will help in the case, for example, if you have, say, 100 documents, and only 5 of them contain the term quantum physics. If you search for that term, you probably really want to upweight the word quantum physics, because those are the only places where those words appear. And you can make the search words better. Finally, in order to account for the differences in text length, as longer documents tend to match more of the words by probability, we have a normalization term to sort of like make sure that the shorter documents also get their time to shine. Once we calculate the score of all these, then we can have a ranking of which of the documents do you want. Finally, there is a third approach, which is used to handle the case where, let's just say you use some kind of idiom or weird phrases, or things that you can't really use with a kind of dictionary or some kind of like, or that the phrases are totally different, but the meanings are actually the same. And this is leveraged through the use of some AI model, especially the LLMs. So what you do is you sort of like feed it through the model, and then we take some intermediate representation, and then we hope, this really depends on the model, that this intermediate representation would represent the meaning of what you are searching. So we take the query, feed it through, and take each document and feed it through. Then we can represent all of them as a vector, which will look like some kind of arrow. Then, by measuring the distance, usually using cosine distance, which is what is the difference between the angles, you're able to tell which of the documents are more similar to each other. So far, at least from my experience, the vector space search model, although it has the potential for catching more of the difference, more of the documents, is actually not as good as doing the BM25. For this reason, systems that uses word-based search is actually still more popular in general. However, the word-based models aren't really good at sort of like making sure that the number 1 to number 5 ranks are actually things you want to search. So in order to compensate for this, we tend to use other models to sort of like re-rank them. If you're interested in this, you can look into algorithms that does pairwise ranking or something like learning to rank. All right, then. I know this is relatively early, so that is going to be the end of my content for this week on how LLMs remember. Any questions so far before I go into this week's questions? That was a loaded sentence. Yes.
People use the vector, like the embeddings to re-rank.
That is. Oh, okay. Restate the question. Okay, so the question is whether or not we use the vectors to do the re-rank. That it is one way to do it. However, most of the time in say learning to rank algorithms, you either give some sort of a ranking list. So you sort of just, you don't really say what is the raw score, but you just say what is the ranking itself. That's one way. But of course, there are some algorithms that give you a score and you just rank them by a score. And sometimes those use like a vector algorithm.
I have a question about semantic memory. So I know there have been a lot of studies in semantic memory in people where they've studied likelihood of being able to recall a fact after repeated bouts of learning it. And there's now algorithms that are used, I think like apps like Memrise, or you can found in psychology for the last few years, for how often you need to, how long you should wait before a repeated bout, like if you're learning a language, for instance, and your likelihood of retaining something from the bouts.
Mm-hmm.
Do you know if anyone or you have like done any similar comparison between like the number of occurrences, for instance, of Frankenstein and the corpus of GPT-4 to increase accuracy, or whether there's like similar statistics or a similar curve for information retention based on like either number of occurrences and corpus or number of epochs?
So the question, so to repeat your question, is that okay, so it's a question whether or not like there is a correspondence between the number of times humans practice things in the psychology literature, as well as like how do you space practice versus how many times an LLM needs to see specific data in order to remember them.
Yeah, so it's called the Ebbinghaus forgetting rate.
Mm-hmm.
And it's just basically information is lost over time at repeated bouts increase accuracy.
Mm-hmm.
And there's statistics to it where it's like, so for instance, if you learn something, you've been exposed to something once, you're going to end up over time ending at maybe like it looks like 10% likelihood of remembering something, and then by 2 bouts like 30%, 3 bouts like 65%, 4 bouts like 90%. I'm curious, so like Frankenstein's a good example. It's very likely that like it occurred both in some published PDF that ended up in the GPT-4 corpus, but also Project Gutenberg. And so maybe in general, things like the Pledge of Allegiance probably occurred like 50 times in the corpus.
Mm-hmm.
So I'm curious if you know whether there's similar statistics, in terms of number of occurrences versus like the fidelity. Same reason that the first paragraph of Frankenstein is probably all better.
Okay. So to repeat your question for the people online, whether or not there is a similar occurrence of like if an LLM sees something very often, it is more likely to remember, in the same way that in humans, where if we repeat something, then we're more likely to remember them. I do not have concrete numbers, but a lot of what I know seems to suggest that the more you repeat it, the more it is able to remember. However, there are some nuances in terms of like the difference between like when an LLM is trying to remember something versus a human trying to remember things, because not only is because there is a concept of spaced practice in terms of when human tries to remember things, which is if you try to just sort of like cram the same thing over and over and over again, you're less likely to remember than if you repeat the same number of times spaced over a different amount of periods. And then some of the theories as to why this happened is that you're remembering the same thing, but in different contexts, and your brain is much more able to sort of like extract things that are relevant. In terms of LLMs, because the sort of like the text or like the context is sort of like more limited compared to a human that has a lot more things going on, I'm not sure how much of this would like hold, would it actually help with, because there are less variations that can actually happen, which might help with recall, or because there are less difference in context, it is less able to extract out what is actually important. So I am not quite sure.
I think you had a virtual question.
Yes, what is the virtual question?
So we have an exciting question from the students. Is it possible to train LLMs to prioritize remembering user input more than external facts? And do you think that could make them more human? I have a quick personal comment.
Mhm.
I don't need to hijack this question, but I think it's a really exciting question in the sense that it's one of the practical questions that Gridspace trying to back to raise.
Okay, to repeat the question, how do you teach an LLM to prioritize certain user
User input over like general facts.
user input over general facts? I guess I need to clarify, as in when you're talking about user input, are you talking about cases where you are training the model and you have some live user input and you're changing the weights? Or are you referring to the case where you are, say, talking with ChatGPT and that user input is in the context? I was thinking of the second one. So it is hard to say, like, because it is already in the context, and that context is already fixed. Like every time it is doing a calculation, the LLM is already looking at that. But whether or not the LLM is actually prioritizing that sort of input might be the issue. So that would really depend on sort of, say, how you're prompting the model. Sometimes maybe the model might be looking at the prompt more than other things, as well as sort of like how you're training it. So I would say it's a hard question to say, but there are multiple approaches to this. Any follow-ups?
You could fine tune it.
Or you can fine tune it to do a specific. Yes.
This relates to like how we design the knowledge base.
Mm-hmm. Yeah, so that relates to the knowledge base. However, I do think this is a bit more relevant to the lecture on next time, and I think that it's probably easier to discuss once we have the context of that lecture. Yes.
It seems to me that episodic memory is typed in space and time. So in contextual memory, so to speak, you'd have to kind of tag those bits with time, or all of your contextual memory is going to be always located at like the instance. That kind of correct.
So the question is, for semantic memory, you need to sort of like tag it with location and time. Sorry, episodic memory. You need to tag it with location and time. Otherwise, it will have some kind of like, it seems to be at the same place. Or
in context, if you don't give it a time, then all of its contextual working memory is in the same time.
There's no sense of time.
Yeah.
Yeah, it has no sense of time. Yeah, so one of the main differences, for example, if you're having like different Yeah, that is the case. For example, let's just say if you're doing like some kind of ChatGPT style chatbot, you're sort of like tagging along in the context, like who was talking earlier. Although it doesn't really give information as to like what time. So if you ask like how much time has elapsed since it's not really gonna know. Another way you could think about it that sort of parallels between how humans look at time versus how, say, LLMs look at time in, say, a very small time frame is that there is a part of a brain that gives some kind of like a clock signal to the hippocampus. So it has something called like a theta wave that sort of like oscillates up and down, and the brain uses the information to sort of like see like where the information is at different points in time. So the parallels to LLMs is that in the transformer model, we have positional embeddings, which sort of says which token comes before and after. And then in the original transformer model, we use sine waves and like sort of like that go sort of like oscillates up and down. It is more complicated than that. We use multiple sine waves. I won't go into the details, but that seems to be some kind of parallel for a short time frame. Now, if you're talking about, say, a long time frame, for example, like between like days or like multiple years, that's going to be different. And I don't think in many of like a pure LLM doesn't really have that, but we could add them in as some kind of like other feature.
Follow up on that, that's,
Mhm.
as well, like, so in that, you can also have episodic memory, I guess, in the weights of the LLM, right? It can remember an event if it was memorized. There's some kind of trade-off between like the number of parameters you have and how much, let's say, the model weights have episodic versus semantic memory. Like kind of memorization versus learning.
So your question is, if we add some kind of like a timing context, is that correct? When we're training so that it can have episodic memory?
Well, if let's say it's remembering an event if it's memorized an event and if it's got like not much data in it,
Mm-hmm.
memories just very specific instances.
Mm-hmm.
That's kind of episodic, right? It's not general info, it's an actual example of the context of where it learned a thing.
Okay, so to repeat, if you sort of like train it once and it hasn't really like abstracted away all the other things and it sort of has an episodic memory, kind of, yes, because that's how you get sort of like regurgitation.
Right. So you could almost like vary how much like episodic versus semantic memory it has with its weights, perhaps.
Perhaps, yeah. So we could make it such that you can let's say that, is there a trade-off between like having it like vary between episodic and semantic? I think there is, and it sort of goes into the discussion of between like I think it's like the bias and variance trade-off, because like I'm not sure is that the correct way to say it, but if we have it being able to regurgitate things very efficiently, then it's not going to generalize that well. So meaning that if we ask it something, it is not likely to sort of like extract away just the facts that we need. So there might be a trade-off. It will also depend on sort of like how you construct the memory. There's in fact another paper where you can sort of like have like a transformer model act similarly to how a hippocampus would work on that, but that might not be too relevant to this discussion. All right then, so for this week, I have 3 questions. One, which is the one that I have discussed earlier, is why is it that ChatGPT was doing poorly on the 3-back task, even though it's supposed to have superior, in big quotes, memory to humans? Second question is, as LLMs gets larger and larger and trained with more and more data, how would you expect the models to perform on each of the memory categories? Finally, sometimes LLM remembering stuff can be bad. For example, if it's remembering some private data, health data, or some copyrighted data. What are ways that you can alleviate this? All right, then. Thank you very much. And see you.
Hello, thank you for calling Gridspace's YouTube channel. Did you make sure they liked the video and smash that subscribe button?
Yes, I did.
And ask them to leave any questions or thoughts in the comments. It helps me a ton. Thank you for watching, and if you'd like to talk to me yourself, go to gridspace.com and click on any one of our demos. Thank you, and talk to you soon.
Thank you, Grace.